State error and static error constant. In this session, we will discuss about how to find the steady state error, and also we will discuss about the static error constants. And before that, there is a concept that is type number of control system. And first of all, consider a control system that having a block diagram shown in the figure. And here the g of s is the open loop transfer, open loop gain, and h of s is the feedback gain, and the output of the summer is error signal, and that error signal then goes to the open loop gain g of s, and the corresponding output is c of s, or the response is c of s, and input is r of s. And in this figure you can see that g of s into h of s is the loop gain. That means when g of s is multiplied by h of s, that will give the loop gain, and we can write the loop gain as the ratio of two polynomials. So it has a general form: g of s into h of s is equal to k into p of s by q of s. That means it is written as the ratio of the two polynomials, and that will have in the roots k in that is having the roots like that is equal to k into s plus z1 into s plus z2 into s plus z3 etc. divided by s raised to n into s plus p1 s plus p2 etc. etc. See here, the numerator contains the zeros z1 z2 z3 etc., and the denominator contains the poles p1 p2 p3 etc. Zeros means the zeros are the values of the s for which the function g of s and h of s will having the minimum value 0, and poles are the values of the s in the denominator polynomial for which the values of the function g of s and h of s will be infinity or maximum value. And here k is a constant and n is the number of the poles at the origin, and based on the value of n, we are classifying the system as type 0 system, type 1 system. If n equal to 0, then the system is type 0. If n equal to 1, then the system is type 1. If n equal to 2, then the system is type 2. Similarly, we can have different values of n, and corresponding to there will be different types. So next we will go to the equation for steady state error. So we can represent the steady state error as ESS, and the steady state error is defined as the value of the error signal E of t when the time value will be E tends to infinity. That means steady state error ESS can be written as that will be equal to limit t tends to infinity E of t. And we will get this is we will get the value of limit t tends to infinity into E of t by using the final value theorem of Laplace transform. That means it states that if there is a function f of t, then limit t tends to infinity f of t will be equal to limit s tends to 0 s into f of s. That is the final value theorem. And using this final value theorem, we can find out the value of limit t tends to infinity E of t. So steady state error ESS equal to limit t tends to infinity E of t, that will be equal to limit s tends to 0 s into E of s. So that is obtained by the final value theorem. So if you are asked to find out the steady state error, so you can write the steady state error will be equal to limit t tends to infinity E of t, and that in turn will be equal to limit s tends to 0 s into U of s, where the value of value of E of s can be written as E of s will be equal to R of s divided by 1 plus G of s into H of s. And this is a very important equation. You should by heart this equation, and it will be useful for doing problems. So the steady state error can be obtained by limit s tends to 0 s into f of s into E of s, where E of s equal to R of s divided by 1 plus G of s into H of s. So next is the static error constants. There are three static error constants, that is positional error constant Kp, velocity error constant Kv, acceleration error constant Ka, where the positional error constant Kp will be equal to limit s tends to 0 g of s into h of s, and velocity error constant Kv equal to limit s tends to 0 s into g of s into h of s, and acceleration error constant Ka equal to limit s tends to 0 s square into g of s into h of s. These are the three static error constant, and you can find it out from the product of g of s and h of s, and that in turn directly give the positional error constant. When we are taking the limit s tends to 0 of g of s and h of s, it will give a positional error constant. So next is the steady state error when the input is unit step signal, and this is a university question. That means it is asked that you have to find out the steady state error when the input signal is unit step signal. So here the input is represented by the letter R of S, that is a unit step signal, that is R of t will be 1 and R of S will be 1 by S. Okay. So you are asked to find out the steady state error. First of all, you should write the equation for steady state error, that is steady state error ESS equal to limit s tends to 0 S into E of S, where E of S equal to R of S divided by 1 plus G of S into H of S. So this is the equation for steady state error. And here R of S is given, that R of S is the step input signal. So for the step signal, R of t will be equal to 1 and R of S will be equal to 1 by S. So we can substitute the value of R of S and we can cancel the common terms, and so we will get the limit s tends to 0 1 divided by 1 plus g of s into h of s, and this limit s tends to 0 can be applied to this quantity, that is g of s into h of s. So we can rewrite the equation like this, and here you can see that this quantity, that is limit s tends to 0 g of s into h of s, is kp, that is positional error constant. So you can write it as a 1 by 1 plus kp. So when we are finding out the steady state error by giving a step signal input, so we will get the steady state error as 1 divided by 1 plus kp, where kp equal to limit s tends to 0 g of s into h of s, and this constant kp is called positional error constant. And we can find out the positional error constant and a steady state error for various systems like type 0 system, type 1 system and type 2 system, etc. So next we will do that thing, that is for the type 0 system we know that the equation for kps limit s tends to 0 g of s into h of s. For the type 0 system we know that this product can be written in the form of k into s plus z1 s plus z2 s plus z3 divided by s plus p1 s plus p2 s plus p3. You know that since it is a type 0 system, so the powers of s raised to n will be equal to s raised to 0, so that will be equal to 1, so there will not be the term of s. Okay. So when you are applying the limit s equal to 0, then you will get the value like this. Okay, that means this is a constant value. So steady state error in the case of a type 0 system will be a constant. So when the input is step input signal, and for the type 0 systems the steady state error will be a constant value. Okay, then we will analyze the type 1 system, and the type 1 system will have g of s and h of s like this. You know that in the case of type 1 system there will be a quantity s. Okay, because s raised to n, where n is the value of type number, that is type is 1, so s raised to n will give you s. So at the denominator side there will be a quantity s. Okay, so you can write the steady state error as you know that this is the value of kp when we are giving the limit value s tends to 0, then this quantity will be equal to infinity. 1 by 0 will be equal to infinity, that is the value of kp, and kp in the case of steady state error kp will come to the denominator side, so the 1 by infinity will be equal to 0. So for the type 1 system, when the input is unit step, then the steady state error will be 0. So in the system with the type number 1 and above, for unit step input the value of positional coefficients or positional coefficients error constant or positional error constant will be infinity, and so the steady state error is 0. So this is an important question, and this is asked for the university examination question. Okay, next we are giving another input, that means a ramp signal input. It is a standard signal and we are giving to a system a ramp signal is given to the control system, and we are asked to find out the steady state error when we are giving this ramp signal as the input. So we know that the steady state equation will be equal to ess equal to limit s tends to 0 s into E of s, where E of s is equal to R of s divided by 1 plus G of s into H of s. When the input is ramp signal, then R of s will be equal to, we know that R of t will be equal to t, then R of s will be equal to 1 by s square. So we can substitute the value of R of s, so we will get the steady state error equation like this, okay. So in that common terms will be cancelled out, so that we will get the limit value like this. And if we are substituting, see here the limit value is limit s tends to 0, 1 divided by s plus s into G of s into H of s. Here you can see that this limit can be applied to this denominator side, so that will be equal to 1 divided by limit s tends to 0, s into G of s into H of s. So this value will be equal to the velocity error constant, that is kV. So in the case of control system with when in which we are giving the ramp signal as the input, then the steady state error will be equal to the velocity error constant, that is 1 by kV, where kV equal to limit s tends to 0, s into G of s into H of s, and the constant kV is called velocity error constant. And next we want to find out the steady state error in the case of type 0, type 1 and type 2 cases. So first we will take the kV value. Once we obtain the kV value, the inverse of that kV value will give the steady state error. So for the type 0 system, we know that we have the equation for kV as kV equal to limit s tends to 0, s into G of s into H of s, and we can substitute for G of s into H of s quantity as k into these quantities. See here s is in the kV expression, and other terms denotes the G of s into H of s product, and when we give the value of s as 0, you can see that this quantity will become 0. That means 1 by kV will be equal to infinity. That means steady state error will become infinity. For the type 1 system, similarly we can write the equation like this. For the type 1 system, kV will be equal to limit s tends to 0, s into G of s into H of s. That is a common equation. And we can substitute for G of s into H of s for the type 1 system, and here there is an s term in the denominator for the case of type 1 system, and we can substitute the values for s tends to 0, so we will get a constant value like this, okay, because s will be 0 and the rest of the quantities will be like this. So steady state error in the case of type 1 system will be equal to 1 by kV, that will be a constant. Hence type 1 systems, when the input is unit ramp, there will be a constant steady state error. Similarly, we can find out the steady state error in the case of type 2 system, and we will make the substitution like this. And here the difference is that since it is a type 2 system, so the power of s will be 2. So we can substitute s tends to 0, so we will get the value of kV as infinity, and so steady state error will be 1 by kV, so that will be equal to 0. So in the systems with the type number 2 and above, for unit ramp input, the value of kV is infinity. So the steady state error is equal to 0. So we have discussed about two cases for finding the steady state error, and one by giving the step input and other by giving the ramp input. Similarly, we can give other standard signals such as parabolic signal as input, and also we can give impulse as input, and also we can give sinusoidal wave as input. So in the similar way you can find out the solution for steady state error, okay. So this is all about this topic.